Hey guys, thank you for coming. Before we get started, a couple of requests. First of all, can you please set your phones to silent mode? Also fill out your evaluations. You should have got an email with the link to the evaluations, so please fill those out. And it says here, tweet Khronos Dev Day for a free t-shirt. I don't know if that's still happening, but you could try that. Okay, my name is Jack Porter, and I'm here with Kostiantyn Drabeniuk. I'm from Epic Games. I'm the Unreal Engine mobile team lead. And Kostiantyn's from Galaxy Game Dev at Samsung. And today we're going to talk about bringing Fortnite to mobile devices, especially the second half, especially focusing on the Vulkan improvements and optimizations. And so in the first half of the session, I'm going to talk about the scope of the problem and why bringing Fortnite is a particularly difficult case. Bringing Fortnite to mobile is difficult compared to maybe another porting other games. Specifically, I'm going to talk about performance and memory, and then I'm going to talk about some of the features and enhancements we've added to Unreal Engine recently that are improving things, especially for Vulkan. And the areas I'm going to touch on are things where they intersect with the Khronos APIs. In the second part, Kostiantyn's going to talk about the Vulkan optimizations and how, with some specific examples of how they were able to optimize performance and remove hitching. So the scope of the problem is that Fortnite for mobile is the same game as Fortnite on other platforms. And so, because we set out to support cross-play on all of these platforms simultaneously, we're really constrained about what we can do to the content in order to make this game work on mobile devices. And we have very regular updates, maybe every 2 weeks. There'll be a lot of new content going out to all platforms, including mobile. And anything that affects gameplay has to be fully supported on mobile. So we can't just cull objects, we can't reduce the draw distance, engagement distance has to be exactly the same. Also, we're very conscious of keeping Unreal Engine and Fortnite in sync. This has a lot of advantages for all of our partners using Unreal Engine. We don't want to make Fortnite a special case with the engine hacked to pieces to make it run. We want everything that we're doing to be usable and supportable by everybody else using Unreal Engine 4. So at the very start, I need to compare, what we can do to simplify things. So if we look at the features we use on desktop and console, we have a deferred renderer, we have movable directional light for time of day. With CSM, we have some distance field shadows. We have skylight and sky reflection with some ambient occlusion, some dynamic point and spotlights for effects, explosions, that kind of thing. We have a physically based material system where all the materials are created by, pretty much exclusively by artists and without any program intervention, with some special cases for subsurface scattering and foliage, some effects there, and on desktop we use temporal anti-aliasing. But if we compare that to what we have available on mobile, the very first thing we've done is simplified the renderer to be a forward renderer. We don't think with the kind of flexibility that Unreal Engine is able to provide in the material system that we have enough width available for any kind of decent deferred rendering with a wide enough G buffer. So with that forward renderer, we have movable directional light, cascading shadow maps, and we've lost some of the effects for the skylight. We have a few dynamic local lights, but we've lost shadowing. The physically based material system uses the same artist-generated inputs, but we have an approximation for that. And we have some slightly simplified versions of our effects and post-processing. And we can use MSA on mobile devices. The second major change we can do is in terms of aggregating content with a hierarchical LOD system. Our biggest problem on mobile, which I'll get into in detail in a second, is is draw calls, and because we have so many draw calls, aggregating content is one of the best ways to deal with that. But of course, Fortnite is a game where destruction plays a big part, and being able to destroy objects means your proxy representations have to be destructible as well. So we have a small system that we can tag the destructible pieces of the geometry and remove that from the proxy assets. Okay, so those simple things out of the way, this is the scope of the problem as it remains. We've still got about 80,000 objects on the island, 10,000 of which are typically loaded based on our content streaming system. Around 800 draw calls, but it could be 2,000 peak with a lot of firefights and explosions going on towards the end of the game. And we could have 600,000 triangles on the high end where we have most of the effects and all of the foliage turned on. One of the beauties of Unreal Engine is our artists can create many shaders using many materials, using whatever techniques the artists feel like they need. And the downside of this is that we have a huge number of shaders and PSOs. And I'll get into some details about that as well. Finally, memory is another big problem, and I'll talk about some of the areas we've had to work on that. So the main challenges are performance and memory, and then I'll talk about device compatibility, especially as it relates to Vulkan. On the performance front, we can divide it into the CPU and the GPU. And on the CPU, most of the problems we've had has been graphics API overhead due to the number of draw calls that we have. We've got a couple of strategies there. We can use an improved graphics API like Vulkan, and adding an RHI thread, which issues API calls has been the other main area we've reduced the overhead of the API. We can also reduce the draw calls and the state change with improved occlusion culling, better sorting to reduce the state changes, and also instancing is something we looked at during development. On the GPU side, of course, we can modify content, we can scale resolution and frame rate, and there are some renderer improvements we can make that will reduce the GPU. Kostiantyn's going to talk about some of that in the Vulkan side, as well as I'll talk about some of the improvements we've recently made to Unreal Engine to allow that. So for the draw call, we have two main threads in Unreal Engine. The render has been set up, so you've got the game thread updating the game state, and then we have a render thread that takes some proxy update information from the game state, and then walks the scene graph and renders the scene using the steps there. So in that really simple setup, top half here is the game thread, the bottom half is the render thread. So here's the game thread. Halfway along, we're kicking the rendering off, and the rest of the time we're sitting there waiting for the rendering to finish. And the render thread calculates visibility, it walks the scene graph, and it issues a lot of API calls for those visible objects, and then it waits for vsync and swaps the buffers. So we found a very significant part of the render thread time is spent inside GL and somewhat inside Vulkan, especially when there's a lot of state change. So we find, draw calls themselves are not a great measure of how what the cost is going to be. You can have a bunch of draw calls all in a row with no state change, and it's almost the same as if they're instanced in terms of performance. But the state change we pay usually turns up inside GL draw elements, so the driver is doing a lot of work at that point to set things right for the next draw call. And so we could use instancing at this point, but in order to use instancing, you have to sort by state, and we get 90% of those benefits simply by sorting by state correctly. So an improvement here was to add what we call an RHI thread. RHI is Render Hardware Interface, Unreal Engine's OpenGL or Vulkan or on other platform, different API implementation. And the idea is to make sure that the rendering code never has to wait for any API calls to complete. So when we create resources or we update resources, we can return immediately with a proxy handle and then continue on and have the RHI thread pick up and replace the handle with the correct API handle. So the same thing in the 3-thread setup. We have the game thread as usual. One difference is instead of waiting on the render thread, it's waiting on the RHI thread from a previous frame. The render thread, which calculates visibility as before, but the time spent in queuing draw calls to the API, the time spent executing draw calls is a lot reduced because all it's doing here is enqueuing the request to do the draw call to the other thread. And here we're waiting for the next frame from the game thread. So overlapping in parallel, we have the RHI thread, which sits there. It updates resources, it changes state, and it issues draw calls using the GLES or Vulkan API. And finally, we wait there for swapping. So we synchronize in two places. First of all, we need to wait on occlusion queries. And our visibility code, if you recall in the previous slide, was happening in the middle render thread, but occlusion query results are going to be available in the RHI thread sometime later. We do have an extra frame of latency when the RHI thread is enabled for our occlusion queries. I'll talk a little bit about how we address some of that synchronization issue in a little bit. The game thread also simply waits on the RHI thread to make sure we don't get too many frames ahead. So for GLES, these are the scale on the left is in milliseconds, so the blue line is 33 milliseconds. That's the overall frame time. The red or the orange color is the time spent in the render thread. So in the top half, that's the combined visibility, scene graph, walking, and API calls. And in the bottom, you can see we've added the extra green thread, which is just issuing the API calls. So that's been a big win for us. So the other thing we can do, of course, is change the API that we're using for rendering. Our GLES requirements are ES 3.1 with ASTC textures, relatively high minimum spec compared to some older devices. We could probably expand that, but at the moment that corresponds quite well to devices that are performant enough to run Fortnite. There are some extensions we require, but on the Vulkan side, we don't have any very strict requirements, but we have whitelisted devices based on the performance we've measured. And that's unfortunately because Vulkan is not a clear win on especially older devices. So lack of driver maturity on older devices leads to poor performance. And I've got to say that things have really improved, and current modern devices are great. Problem with that is that modern devices are also very performant. So the CPU gains we're getting from Vulkan are reduced simply by the nature of these devices being very fast. There's also some extra GPU cost from our Vulkan implementation, and I'll talk a little bit later about a couple of the improvements we're doing, and Kostiantyn's also going to talk about reducing that GPU cost. But in the end, many of the devices where we'd love to be using Vulkan, devices with poor CPU performance, which is really limiting our draw call counts, as precisely the devices that we're unable to benefit from. So, we're hoping as time goes on, there's been improved adoption and improved driver quality. This problem will go away, but right now, Vulkan has not been able to solve problems for us on the very low end of devices that we'd really like to be able to support. So currently we're shipping Vulkan only on some high-end devices. It's also a win on pretty much all the modern, or this year's flagship devices based on 845, 855, and Mali G76 GPUs. And so I expect we're going to enable it by default on a lot of new phones this year. But what Vulkan is enabling us to do is to push quality and performance on the high end. So we're intending to make use of Vulkan to actually improve the quality somewhat for those very high-end devices. So we still do find a benefit from using an RHI thread on Vulkan. As you can see, I'll go to the comparison here. As you can see, the overall RHI thread time is quite reduced. It's it's around 30% faster than OpenGL ES in just its raw calls. We're still getting that benefit from having that extra RHI thread as well as the render thread. So another way to improve the draw call cost is to draw fewer objects. And so occlusion culling is the best way that we've used in Fortnite. And before Fortnite shipping, we didn't actually have hardware occlusion working at all on mobile. So this was an area where we have spent quite a bit of time trying to improve and optimize. Obviously, the idea is to render some proxy geometry against a depth buffer wrapped in a query in either GL or Vulkan using those APIs, and then checking if any of the pixels of the proxy geometry were rendered or would have been rendered, or the whole lot was culled away by the depth buffer. And using that information, we can decide whether or not we want to render the real geometry. But we need a depth buffer to test against, and so on mobile we don't use a depth prepass. We felt the amount of geometry we have, certainly the extra draw calls and the extra vertex count is probably would make that infeasible to do a separate depth prepass. So we cannot render our occlusion queries right at the start of the frame as we would on PC and console. And so we have to render them a little bit later. So we're rendering them directly after the base pass. So we have an extra frame of latency before the visibility information 2 frames later can actually make use of the occlusion results. As I mentioned just before, thread synchronization between the RHI thread and the render thread has been problematic for occlusion queries because we can only wait for the occlusion queries on the RHI thread. And the results are needed on the render thread where we actually make the visibility determination before we walk the scene. So something we're doing now is to poll both GL and Vulkan. We poll, as we enqueue commands to the RHI thread, we poll to see if the occlusion queries we issued previously have completed. So for example, the top is the render thread, the bottom is the RHI thread. As we're uploading extra commands to the RHI thread, we periodically poll to see if the occlusion queries have finished. And as we go along, eventually the results for those occlusion queries will be available. And most of the time we find that the render thread, by the time the render thread needs them, the occlusion queries are done and we don't need to block. On the implementation side, both under GLES and Vulkan, we find certain devices have a limited number of outstanding occlusion queries that are supported. Ideally, we'd have an occlusion query per object that we could know for sure whether that particular proxy geometry needs to be rendered as real geometry. So we've had to virtualize how we implement the occlusion queries. Kostiantyn's going to talk a little bit about how we reuse the occlusion queries for Vulkan. We also have a round-robin system for aggregating geometry at a higher level in Unreal Engine that is used to aggregate this proxy geometry. So getting onto memory, as I mentioned, artists create the majority of the shaders through the material system that we have in Unreal Engine. It's a node-based graph that we combine with some handwritten HLSL code, and then we run it through an HLSL cross-compiler to generate GLSL. And on Vulkan, we go through GLSLang and all the way to SphereV from that. So one of the problems is, even though there's a single artist-generated material, we have a huge number of permutations that we need. For every kind of mesh that we want to render this material with, we need, which we call a vertex factory, we need different permutations, and we need different shaders depending on the operation we're performing. For example, our forward pass, we have multiple versions depending on the lighting setup. If an object is completely in shadow, completely without any shadow being cast on it, we can use a faster version of that shader without doing any CSM lookup. So we want to have 2 copies of that shader for that particular material when we're rendering the base pass. We also need shaders to generate shadow depths. We can share those shaders amongst opaque objects, but objects with alpha-tested masked geometry require individual shaders for the depth rendering for the shadow maps. And of course, we have translucency and effects. And the result is over 28,000 individual shader programs, which is a crazy number. So the set of shaders that we need, we have some automated methods to gather, as well as some manual gameplay we can use to gather the actual PSOs required for rendering the game. And so we've reduced that to a still large set of shaders. So on GL ES, we have to compile at runtime. So at first launch of Fortnite, we compile all the shader programs and then save out binaries. And then on subsequent launches, we can recreate those shaders from the binaries. So ideally, we'd just recreate all of these and we'd be good to go and would never have any hitching during the game. All the shaders programs would be prepared. But even though the binary data is in the order of 20 to 30 megabytes, they balloon to more than 10 times their size inside the drivers on certain devices. So we found it's just not feasible to keep 400 megabytes of shaders in memory, so we need to have an LRU system. And we have some different strategies for the LRU for how we want to evict the shaders and which shaders we want to keep around. So we have a few options. We could simply do strict least recently used based on some number of shaders that we have in memory, or perhaps an estimation of the shader memory. And we do that on some devices. On other devices, we can watch for when objects that are using a particular shader are being destroyed, and then, if there are no more objects existing in the world with that particular shader, then obviously we don't need it, so we can destroy it. But unfortunately, that use case doesn't work for something like particles, where you're in a firefight, set off an explosion, you want the explosion to happen immediately, and that's the time you certainly don't want to hitch. When we want to restore the shader, we've got a few options. We could go back to storage, or we could use a compressed memory buffer. On Arduino, the total shaders are only about 20 megabytes compressed, so it's feasible to keep that in memory, and we just use the compressed version. On Mali devices, we keep binaries in RAM, either as a binary or as a shader, and then switch between the two. It's quite quick with that particular GPU driver for us to have it recreate the binary on demand rather than keeping them around. So we have the same kind of issue on Vulkan. Kostiantyn is going to talk a little bit about the large memory savings that shader handling that we've been able to make for shader handling on Vulkan. We gather PSOs exactly the same way we do for GL ES, and we create a pipeline cache at startup instead of shaded binaries. We also have a runtime LRU. The final section I'm going to talk about is some recent Unreal Engine 4 rendering improvements that specifically relate to modern graphics APIs like Vulkan. Unreal Engine's been evolving for a long time, but we've recently done a few some refactors to improve some of these things. And the first thing is explicit render passes, as well as Vulkan subpass support, and finally there's a high-level rendering refactor. So for render passes, Unreal Engine used to simply inform the graphics API RHI layer when it needed to set a new frame buffer or set a new render target, and then the RHI would have to guess whether or not it's going to need a new render pass. We had some flags there that we would try to convert into the usage masks for the render targets, but we've recently refactored the high-level code to explicitly set render targets, render passes. And so in the latest version of Unreal Engine that's coming out in early next week, I believe, the RHI functions for explicit render passes will be enabled in the mobile renderer, and we're making use of that to remove unnecessary transitions. For example, between our base rendering pass to translucency and post-processing, we want to avoid unnecessary transitions and keep everything inside the GPU core. Related to this is something that's a bit more Vulkan specific, and this is subpasses. And our use case for this is anywhere where we need to access the existing fragment depth value, the existing scene depth value when we're rendering a new fragment. And this is for techniques like soft particles, where you want to blend based on how close it is to geometry behind it, or deferred decals, where we need to convert the depth value into, or the existing scene depth value into a UV value for the decal. So we use frame buffer fetch in GL ES, and we can either get the depth from the previous, we would store it in the alpha channel, or we could fetch the depth directly if that was available using the fetch depth stencil extension. And then we would compare the fragment depth against the existing depth. So the Vulkan way to do this is to set up subpasses where you say one subpass is dependent on the other, and you can map access to that depth information from the first subpass to the second subpass. This is a very Vulkan-specific feature, which, as well as being only applicable to mobile GPUs, simply trying to take advantage of this idea in a tile-based GPU where you want to keep everything in the GPU core. And so instead of adding just general Unreal Engine 4 support for subpasses, we've added some hints that following pass will make use of the depth. We set up two subpasses, and we call next subpass between the two, which on Vulkan we simply call the VK next subpass API. But on OpenGL, we could make use of this hard distinction between the two subpasses to make use of a slightly more optimized version of frame buffer fetch. So in the render dot capture there, as we're rendering, after we render the mobile base pass, we set next subpass, and then we render out deferred decals. Unfortunately, we need an extra PSO permutation to support MSAA. And this is because in the GLSL, when we fetch the existing depth value, when not using MSAA, we don't specify a sample index, but when we're using MSAA, we need a sample index. So unfortunately, a user setting to enable or disable MSAA is going to require alternate shaders. At the bottom is just the GLSL cross-compiler output for that. We implement we generate the depth fetch attachment and then sample it during the decal rendering. The final improvement the rendering team has made to Unreal Engine has been what we call the high-level rendering refactor. And this is a rewrite of the high-level code to allow for much more aggressive caching of static scene elements. So the full state of each draw call, including the bound objects that are needed to render, are cached, and then so the render thread cost is largely reduced, and after calculating visibility, we just need to walk the draw list and apply that state. And this is also coming to Unreal Engine early next week. And because Fortnite and Unreal Engine are so closely, the code bases are so close, these advantages are coming to Fortnite very quickly, very soon. And an advantage of this is because we have the full state available, we can look at we can examine the visible draw list and work out what objects can be automatically instanced together. This does require that all of the per instance constants, for example, the transformation matrices for the particular instances of the mesh, need to be stored in a single buffer that we could look up inside the shader. And we're a bit concerned about exactly how much that cost is going to be for mobile. That's work that we're still looking at. We've previously measured quite a heavy cost inside the shader when doing these kind of lookups. Okay, that concludes part one. On to part two, where Kostiantyn's going to talk in some great detail about the Vulkan-specific optimizations we've made for Fortnite.
Hi everyone, I'm Kostiantyn from Samsung Ukraine Galaxy Game Dev, and today I want to tell you about some optimizations that we made for Fortnite during our collaboration with Epic Games. So before I start, I want to briefly tell you about Galaxy Game Dev. We support game developers all over the world to provide the best gaming experience to customers on Samsung devices. We promote use new technologies such like Vulkan. Also, we help game studios port their game to Vulkan. And one of the companies that we worked with was Epic Games, and I will share some of the results of our collaboration. I'm planning to discuss advantages of Vulkan usage in mobile games, how to get better FPS, and how to get stable FPS. Let's see at video of Fortnite replay on OpenGL. So as Fortnite is a game with a huge number of objects, we mostly have CPU bottleneck because there are so much draw call. Like here you can see that there is bottleneck on RHI thread. And one way to reduce CPU load is port Fortnite to Vulkan. Because Vulkan provides more balanced CPU-GPU usage, lower CPU overhead, explicit control over memory, and synchronization stuff, and other advantages that can improve your performance. So as you can see, with Vulkan, we got much better performance due to reducing CPU load. But just porting your game to Vulkan, you will not get good performance. You also need to make optimization for your games, and it's what we did. So during game profiling by RenderDoc, Systrace, Streamline, Unreal's internal tools, we found many points for optimization. So let's start with first one is descriptor set cache. So we noticed that VK update this descriptor set in total take about 10% time of RHI thread. To reduce the number of updates, solution is descriptor set cache. So in common call stack, before each draw call, update uniform buffer is always called. And uniform buffer, which we already set, is copied to VK buffer. Then we need to allocate descriptor set and update with required data. It's texture, sampler, and uniform buffer. But if descriptor set with this data is already presented in cache, extra allocate and update can be skipped. So as I already said, that in Fortnite there are a lot of draw call, a significant amount of allocate and updates can be skipped. But storing buffer offset inside the descriptor set, you will get a lot of cache misses. Let's see an example how to bind uniform buffer objects. For example, we have a shader with one binding and need to bind a new UBO before each draw call which uses that shader. So first step is to allocate the descriptor set, then we need to update with UBO's offset and simply bind. So step are same for UBO2 and for UBO3. So with this approach, all descriptor set are needed before each draw call. Let's see how to bind uniform buffer object with dynamic uniform buffer. So step are same. At first we need to allocate descriptor set and then we need to update. But in this case we update with some base offset, in our case it's 0, and proper offset will be set at binding time through dynamic offset. Pass it as argument to binding function. So as UBO2 is placed in same VK buffer, we can use previous descriptor set. So in such way, descriptor set can be reused. So and hit rate can be improved by using dynamic uniform buffer. Also, you should be careful with hashing, because don't use Vulkan handle for hash calculation, because Vulkan can use same handle for different types, and also Vulkan can use handles from destroyed resources. So better generate own handle ID and use it for hashing. So after applying such optimization, average number of updates was significantly reduced, and as a result, we got less RHI thread load. Also, we saw in capture from RenderDoc that some render passes were broken. Problem was next. If Unreal set a new render target, need to create a render pass and frame buffer. For render pass and frame buffer, cache are presented. To get render pass and frame buffer from cache, need to calculate hash value from set render target info and get them from cache. If we got same render pass and frame buffer like current, don't need to begin new render pass because previous one can be used. But problem that Unreal set render target before each pass, like here for upscale with clear operation and for slate UI with load operation. It means that hash value for slate UI will be different compared to upscale, and new render pass will be started. So breaking render pass will also have some extra store and load operation. To avoid this was added logic to compatibility checking, and render passes was merged. But even with same load and store operation, render passes can be broken due to extra transition between passes. What happened with the Kali and Run2CC pass. So by removing such redundant transition, render passes was merged into one. So as you can see from RenderDoc capture, such transition not only break render passes, but also add some extra heavy pipeline barriers. So please avoid it. So by merging render passes, performance was improved, and we got a better FPS. So also originally Unreal did extra depth copy before translucency pass. Translucency pass use depth image from base pass like render target for depth test with disabled depth right. Also this depth image is sampled in shader. It means that we need to use depth image like attachment and sample in shader in some time. And if it's not supported, we need to make extra copy and sample copied image. Also we need for copy need to make extra transition. But in Vulkan it is possible to use the image like attachment and sample in shader in same time. So extra copy was removed. So let's talk a bit about occlusion query optimizations. So originally Unreal get occlusion query result for 2 frames back, but in Android we have 3 swap chain back buffers, and it means that size of queue is 2. So getting result 2 frame backs, sometimes waiting happens because this frame can be executed yet. So solution just getting result for 3 frame backs, it guarantees that we don't need to wait. Also, we noticed that it was so much get query result and reset calls because global query pool were used. And with this approach, query for 1 frame can be scattered around the pool. Like here, you can see that query from different frame are mixed. And to request new query with this approach, need to look for free query in pool and then occupy them. And to get result, we need to call get query result for each query separately. Also need to call reset for each query separately. But this approach has extra CPU cost. So solution is just use separate pool for each frame, and with this approach to request new query need just to look for free pool and occupy query from 0 to requested amount in pool. And the result can be got only in 1 call, just specifying first query and query count. And also query can be reset only in 1 call. So after applying such optimization, FPS, we got 2 more FPS and better FPS stability. So as you may know, in Vulkan, index or vertex buffer use VK buffer with device local memory. And it means that direct host access to such memory is not allowed. And to upload such buffer, need to allocate staging buffer with host visible memory, copy data to staging buffer at first, and then copy data from staging buffer to VK buffer with device local memory by copy command. But mobile GPUs usually have unified memory, and it means that we have direct host access to such memory, and extra copy to staging buffer can be removed. So after this optimization, we got less RHI thread load. Hitching. So it's very annoying to get in lags during playing the game. For example, you want to shoot the enemy and get in lags at that time. It's very annoying. And memory, it's also important to optimize because Android can kill your background application if you get in low amount of memory, or you can get some crash during playing the game. It's why we also focus on such optimization. So let's start with first one. It was asynchronous vertex index buffer creation, and original version of vertex index buffer creation used needless RHI thread stall. But Vulkan RHI provides asynchronous index buffer creation, and asynchronous version of such function was provided, and extra weight was removed. And as a result, we got less amount of hitches on render thread. So in Vulkan, texture tags are laid out in platform-dependent arrangement. And to upload such texture, you need to create staging buffer, copy data to staging buffer at first, and then record copy command to command buffer for buffer to image copy, and submit such command buffer to start execution. But in original version, command buffer was submitted after each texture upload, and it means 100 submit, need 100 command buffer and 100 submits. So better record all command to 1 command buffer and make only 1 submit per frame. And here you can see on chart that it was hitches on original version compared to optimized version. And after applying this optimization, hitches was reduced on frame time, render thread time, and RHI thread time. Also, it was problem in hash computing, so hash was calculated from pipeline create info, but this pipeline create info contains pointer and extra data that is not involved in pipeline creation. It's a better idea to calculate hash from pointers because it is possible to have different pointers but same content. So we changed this logic just to calculate hash from all structures, and we added shader key for shaders. Now even if shaders was recreated, shader key will be same. And as a result, we got better hit rate after first session. And also we faced the same problem with descriptor set layout cache. So now we are using actual bindings instead of bindings to pointer. And descriptor set layout and pipeline layout count was dramatically reduced. And also it helped us to save some memory. So Unreal frequently requests to create shader with some shader code like already created shader has. So such duplication also causes PSO cache misses. So we added shader cache and shader duplication were removed. And also memory was saved about 280 megabytes. So in Vulkan, shader model needed only for pipeline creation. And it means that we can skip shader model creation at shader creation time, to create it right before pipeline creation and destroy after. But this optimization can have some extra CPU cost if pipelines are created at runtime. So it also helpful for saving memory. So after applying all memory optimization, memory was saved about 640 megabytes. So if you have some additional question, you can contact me or Jack. Thank you.
How do we deal with textures? We do not use texture atlases. We have individual texture assets for objects or for unique objects that need them. We have a streaming system, so we stream in on a per bitmap basis, so that if, as you get close to an object, we create a new texture, copy the MIP levels across from the existing texture, stream in from storage the new texture. So we simply have a pool of memory that we allocate to textures. That, on a per device basis, we determine, based on its memory at startup, how much we want to allocate to the pool. We have to repeat the question first for the video. So the question is, yeah, we have shaded deduplication in Vulkan, but do we have pipeline, or have we considered deduplicating pipelines?
So we have also cache for pipelines.
Based on the hash on the contents. So
yes. So for hashing, we just using data that needed for pipeline creation, and also, as I mentioned, we added shader key for shaders, and if shaders was recreated, shader key will be same, and we got needed pipeline.
Not actually sure exactly what we do on Metal, but I believe. Is it a completely different random path? Okay.
Hello, I have a microphone now.
Oh, okay. That works.
Could you put your hand back up?
He's at the front here. Yeah. Oh.
Test, okay. What other methodologies were considered when optimizing stuff?
Broad question. We've tried, so we did try several methods of automatic instancing, especially Fortnite's got a lot of trees, and we have a lot of player-built geometry, but we found almost all of those benefits disappeared when we sorted everything to the point where the state we were sorted by state and in a position to be able to automatically instance those things. The high level, and they added a lot of complexity to Unreal Engine. So the high level refactor that I talked about is going to allow that to some degree more than we were able to previously. What else have we looked at? Nothing comes to mind. I mean, we looked at a lot of things, but I can't think of any examples offhand.
Hey, it's loud. Did you run into any mobile-specific bottlenecks, like, for example, fill rate?
For example, what I'm saying?
Fill rate. The number of pixels that you draw.
Oh, fill rate.
Translucency.
So, yeah, after all of these optimizations we've made now, we're now at the point where we're GPU bound on good devices, which is a good position to be in. And we can look at modifying content, modifying shaders, simplifying things to improve fill rate. But especially on low-end devices, we're almost always bound by draw call and API overhead before we're bound by the GPU.
Great talk, by the way. With the introduction of high frame rate phones, such as the Razer phone, does that excite you as far as the possibilities of being able to experience games? Because it does to me, and it's a wonderful feeling to be able to go and play these 120 FPS games. Obviously, it might be a long way, but is it?
Yeah, definitely pushing performance, pushing frame rate is something we're trying to do. We've only just enabled 60 hertz on a few devices that Fortnite is capable of. But yeah, it's definitely an area. Also, dynamic sync rates, so we don't have to wait on vsyncs at all, so we can present frames as soon as they're available. It's definitely an area we'd love to see supported on mobile.
Hi, thanks for the talk. I was wondering if you had any issues when going through the optimization, whether you hit any underclocking problems, because you add more threads, it adds heat, it adds power draw.
Yeah, so CPU is definitely the biggest cause for thermal throttling for us. So really managing what we do on each thread, and we set affinity for which threads we want on bigger little cores to try and manage that. But thermal is mostly a CPU problem. We can, on GPU, you can always address it with, well, it's naturally addressed by reduced frame rate, and the massively parallel problem that rendering means that GPU doesn't suffer so much from thermal as the CPU does. So, yeah, all of the optimization we've done here is also to deal with thermal throttling. Okay, thank you very much for coming, everybody.